Have you ever actually paused to think about how an AI can just conjure up a highly detailed, high-dimensional image out of completely thin air without its processors literally melting down? I mean, it honestly sounds like magic, right? But today, we're going to dive into the exact mathematical workaround that makes this whole thing possible. It's an explainer on autoregressive models. We're going to see exactly how computers generate insanely complex data without totally crashing the system. Okay, to really wrap our heads around the scale of the bottleneck we're dealing with here, just look at this absurdly massive number, 10 to the power of 236. Like, that's the number of possible combinations for just a tiny 28 by 28 pixel binary image. We're talking about a super simple black and white hand-drawn digit from the standard MNIST dataset. Basically, that is the absolute exponential nightmare generative AI faces before it even spits out a single usable picture. Now, if we try to generate that whole image all at once, we'd be using what's called direct sampling. Basically, we're attempting to calculate the probability of a joint distribution in one single shot. Honestly, it's like trying to brute force an impossible bank vault that has millions of interlocking dials. You've got C representing the possible cases, like 256 color values per pixel, and D representing the dimensions, or the total pixels. When you do it this way, the required compute scales exponentially, C to the power of D. The memory and compute you'd actually need to calculate the probabilities for all of those combinations would literally break the system. There's just no way. Section 1, the chain rule, the ultimate cheat code. Okay, let's dive into this, because this is where the underlying math gives us a brilliant escape hatch, taking us from an impossible computational nightmare to something your laptop could actually handle. So instead of attacking that impossible bank vault all at once, the chain rule of probability gives us basically the ultimate heist plan. It lets us take this massive, multi-dimensional joint distribution and completely decompose it into a sequence of smaller, totally manageable conditional probabilities. Basically, we're taking one impossibly huge problem and turning it into a sequence of tiny, one-dimensional steps. Think of it kind of like painting a canvas, or say, writing a sentence step by step. Step 1, the AI generates pixel 1 out of nowhere. Boom. That's just a simple, constant calculation. Step 2, given the context of that first pixel, it then generates pixel 2. Step 3, given pixels 1 and 2, it decides on pixel 3. Do you see what's happening? Every single new piece of data relies entirely on the context of what was generated right before it. It is just such an elegant, sequential flow. Moving on to section 2, linear time shrinking the math. And really, just like that, the chaos of exponential math subsides into a calm, highly organized sequence where the impossible is suddenly solved. So the crucial point here is comparing these two. Direct sampling is one shot, sure, but it demands that totally impossible C to the power of D exponential compute we talked about. But by using the chain rule for autoregressive sampling, our compute cost drops from exponential to completely linear, literally just C times D. We've essentially swapped out a universally impossible calculation for a highly efficient sequence. We're simply running a constant complexity sampling operation D times. And honestly, this is the exact statistical magic that makes deep learning generation possible in the first place. Section 3, building AI engines, autoregressive models. So, we have the beautiful math mapped out on paper, but how do we actually build a computer that can do this? How do we take all this statistical theory and wire it into a physical model? Well, here we have the modern neural architectures that are actually engineered to execute this linear math. We're looking at two major approaches here. First, recurrent neural networks, or RNNs. And second, masked models, like MADE, which, by the way, stands for Masked Autoencoder for Distribution Estimation, and things like Pixel CNN. These are the actual, real-world deep learning machines turning those theoretical equations into tangible AI engines. So instead of relying on these gigantic, impossible probability lookup tables, we just use these neural networks to learn and accurately estimate all of those conditional probabilities we just talked about. And this brilliantly illustrates the mechanical difference between these two main approaches. RNNs use a step-by-step hidden state memory. Basically, they pass a memory vector forward sequentially, accumulating context pixel by pixel, or character by character. Masked models, however, they take a completely different route. They use a standard network structure but simply erase or, mask the paths from future variables. Because they literally block out the future data, they can actually process all the input data in parallel during training without accidentally cheating by looking ahead at the answer. I mean, how incredibly clever is that? But, there's always a catch to this entire process. We absolutely solved the exponential math problem for sure, and thanks to architectures like masked models, our training process is incredibly computationally efficient and easily parallelized. However, when it comes time to actually generate new data, to sample from the model, we're forced to build that output slowly, one piece at a time. Autoregressive generation inherently remains slow because it is entirely locked into that step-by-step sequential chain rule. You simply can't generate pixel 100 without first knowing pixel 99. It's a real bottleneck. Which brings us to a final thought to wrap up this explainer. We've successfully conquered the exponential nightmare using the chain rule, we've scaled compute down to linear time, and we've built the neural architectures capable of actually bringing it to life. But we are still fundamentally bottlenecked by the sequential nature of time itself during generation. So I'll leave you with this. If autoregression flawlessly solves the math, what ultimately limits how fast artificial intelligence can imagine? Thank you so much for exploring this fascinating topic with me today. I really hope this provided you with a clear structural understanding of how these incredible models actually work behind the scenes.